Well, thank you very much for this extremely kind introduction. So I will strive to, let's say, present very shortly, let's say, synergies that exist between fission and fusion devices with, let's say, fission reactors and fusion devices with ignited plasma. And ITER, which is the International Thermonuclear Experimental Reactor that is dedicated to demonstrating the capability of really controlling in terms of temperature, in terms of duration. Ignited plasma is the first fusion device that is really considered as a basic nuclear installation and as such subject to the licensing requirements like fission reactors. As we will see, in fact, commonalities between fission and fusion reactors really increase as we progress towards fusion devices that generate power effectively. The main reason, one of the main reasons why, in fact, there are synergies between, let's say, the current fusion devices and fission devices is because the type of fusion reaction that is the easiest really to generate on Earth is the fusion between two isotopes of hydrogen. And the products of this fusion is, let's say, an alpha particle and a neutron. So this is like a fission reaction that generates neutron, and in fact, in a fission reaction, you are to really sustain the chain reaction. And in fusion, as we will see, the management of this neutron is extremely important. And we can consider that while considering, let's say, the cross-cutting, let's say, the cross-cut of a tokamak, let's say, on the right of the slide, with the plasma being in red. And you can see that the plasma generates power from the alpha particle on the first wall. This is the first surface. But the neutron, the 14 MeV neutron, let's say, escapes the magnetic configuration and just slows down in this medium that is about 1 meter thick, let's say, behind the first wall. And there are two missions that are crucial, really, for this first generation of fusion, deuterium-tritium, is first of all, let's say, to recover the energy that is carried out by the neutron. This is 80% of the fusion reaction. And then the neutron slows down in the blanket itself, and you are to really recover this energy at a sufficiently high temperature to drive a conversion cycle with a sufficient efficiency, meaning the blanket should operate above 300, let's say 400, maybe 500 degrees Celsius. And the other extremely important mission is that this neutron is expected to regenerate the tritium that has disappeared in the fusion reaction. Because the deuterium-tritium fusion are the first kind of nuclear devices for which one of the fuels does not exist on Earth. Tritium does not exist on Earth, and the whole program of ITER has been based on the amount of tritium that could collected from CANDU reactors in Canada. Typically is a few kilograms. And the holdup of ITER is typically 4 kilograms. And I think the whole program of ITER really, let's say, requires about between 5 and 10 kilograms. So tritium does not exist on Earth, and the decay period is 12 years, which means that you cannot accumulate tritium now for a fusion device that will operate in 2050. And then the necessity for the neutron to really regenerate tritium by capture on a lithium, lithiated compound within the blanket is really a key. So regenerating the tritium that has disappeared in a fusion reactor with only 1 neutron to be captured on lithium to regenerate the tritium is a kind of mission impossible. It'd be mission impossible also while considering that the coverage of the plasma is at most 80% because of all the devices, diagnostics, vacuum pumping that is needed. And therefore, let's say the magic is, well, to possibly use, let's say, neutron multipliers like, let's say, beryllium or lead that really can multiply the neutron through end-to-end reactions. Those are threshold reactions, but the 14 MeV neutron has a sufficiently high energy to really multiply the neutron, let's say, and from 14 MeV neutron get about 1.5, maybe lower energy neutrons. So 2 missions for this neutron within the blanket, so really generate power, to generate electricity, and also to regenerate the tritium by ultimate capture on the lithiated atom. And just to give you, to stress the importance of this tritium issue, let's say a typical 1 gigawatt electric reactor would burn about half a kilogram of tritium per day, whereas, let's say, a CANDU reactor, 600 megawatt electric, currently produces about 100 grams of tritium per year. And you see it is absolutely important that, in fact, fusion reactors be autonomous in terms of tritium. Otherwise, the makeup that they would require, let's say, a supporting fleet of fission reactors that be at least the order of the fusion power that is installed. So now I will cover briefly, let's say, 5 types of synergies that exist between fusion devices and fission devices. So the blanket that really is really the medium where this neutron has to be managed, where heat is being deposited, where really appropriate capture of lithium are requested, has a lot in common with fission reactors. And we will see that, in fact, the same design tools that has been developed for fission reactors are currently used for design blankets and demo. Also, some of the safety has a lot in common with fission. Not exactly, there are 3 basic safety functions to be achieved in fission. So reactivity has nothing to do, let's say fusion has nothing to do with reactivity, as in fact, let's say, all has to be, let's say, provided for fusion, let's say, reactions to proceed. And if there are, let's say, the appropriate conditions are missing, so the plasma is just disrupting or disappearing. Whereas the other safety conditions, I mean, the need to cool and also to manage the afterheat is a commonality, as well as in the confinement. And in fact, there are 2 different radioactive materials in let's say, the fusion device with ignited plasma. So tritium, which is a radioactive material, and also activation products. By the way, activation products are the main source of decay heat in fusion. So orders of magnitude are by far less than fission products, but let's say still, even though being low, in fact, activation products still, let's say, release heat once the machine is shut down, and this has to be removed in order to avoid damage to the machine. There are commonalities in terms of materials, in terms of technologies, in terms also in service inspection and dismantling and cleanup. And I will have one word, let's say, back on tritium at the end of my presentation. Just a few orders of magnitude. Let's say in a typical, let's say, fusion power reactor, let's say the surface heat on the first wall is typically half of megawatt per square meter. And there are a part of the first wall that is maybe 10% of the first wall where, let's say, purposely, let's say, impurity ions are being directed, and this surface is exposed to extreme heat loads, typically 15 megawatt per square meters. In terms of energy, the Newton energy load is typically a few megawatt per square meters. Well, globally, a fusion reactor is a kind of hostile, let's say, medium. So hostility having commonalities with those of fission in terms of temperature or irradiation, but also having specific aspects such as a very intense magnetic field and very peculiar geometry. So the first commonality, I said, well, the use of the same design tools for, let's say, Newtonic transport calculations. And you have understood, and in fact, the appropriate management of Newton determines the appropriate heat depositions, and this really controls the temperature in the blanket. And of course, there are requirements to comply with corrosion aspects, as well as appropriate temperature ranges to recover the tritium that is bred in situ into the blanket. So Newton transport is extremely important, and the same tools are being used. So the same tools for thermal hydraulic transport, so the fluid dynamics as well as the cooling of the blanket and the first wall. The same type of tools are used both for the designs as well as for accidental transient analysis. The same tools also are used for the mechanical design of the structures, with some specificity that occur from the fact that, in fact, the power deposition is exponentially decreasing from the first wall to the, let's say, to the outer part of the blanket. And then this causes gradients of irradiation, gradients of, let's say, heat deposition, and of course temperature control, how to deal with that, as well as, let's say, the structural mechanics has also to deal with the steep gradients of irradiation, as in fact there are radial gradients of irradiation because of the, let's say, the fact that the neutrons are not generated within the blanket itself, but come from the plasma. Also of importance are the, let's say, the risks that are associated with tritium, with hydrogen. And there will be typically holdups of a few 10 kilograms of, let's say, deuterium and tritium in 1 gigawatt fusion reactors. And let's say those facilities are subject to damages, and of course the same hydrogen risk type of, at least qualitatively, hydrogen risk that occur for fission reactors also ought to be accounted for let's say, mature power generating thermonuclear fusion reactors. And those codes that are capable of calculating the energy deposition of deflagration or detonations, let's say, linked to hydrogen risk let's say, can be used to really analyze this type of accidents. Now, having a closer look to, let's say, the design of the blanket and the first wall, this is a schematic of, let's say, the cooling scheme. This is a helium-cooled lithium-lead blanket. Lithium-lead alloy is liquid above 237 degrees. And you see that the helium first cools the first wall, that is the most heated part, then heated the front part of the blanket, then the back part of the blanket, exchanges heat with water cooling, and then in a reactor, this water cooling would drive a turbine, and then there will be a heat sink at the end. Radioactive material should be contained is, let's say, in three barriers, like for fission reactors. Certainly for what regards tritium, first barrier is the blanket, the second barrier is the vacuum vessel, and let's say provision could be made in the vault that really supports the vacuum vessel and let's say the magnetic coils, let's say, as to achieve the confinement of the third barrier. Also, radiological barrier should be achieved by appropriate shielding for, let's say, neutrons and gamma. And this is another commonality with fission reactors. So in brief, let's say, for what regards the safety, so there is an inherent safety of plasma, so nothing like reactivity type of accident. However, let's say the cooling accidents may occur as there is a heat generation within the blanket and the first wall, including decay heat necessity, even though orders of magnitude are by far less than the decay heat from the fission products. But activation products still generate heat, and the active removal of this decay heat should occur. And also, you have understood that appropriate confinement with the three barriers, as it is required by the defense in depth, let's say, safety approach, applies to the, let's say, tokamaks with ignited plasma in a more complex geometry. So, and I've shown a few examples of that. And this is very important to proceed with, let's say, convincing the demonstrations to really capable of licensing fusion devices. And as I told you, ITER, even though it is an experimental reactor, so, but it has tritium, it will have, let's say, blanket test modules, and it is really considered as a first, let's say, a fusion device as a basic, nuclear installation, and as such subject to licensing. For what regards, let's say, materials, there are commonalities between materials that have been developed for fast neutron reactors and ITER. There will be little of irradiation in ITER. Well, for the simple reasons that, in fact, the ITER will be, over its 20 years lifetime, will have to survive with the 5 kilograms, or typically 5 kilograms of tritium, so there won't be many neutrons generated. But there will be activation there. So let's say austenitics and steel are really, let's say, mainly used, or other, let's say, nickel-based alloys are really being used for ITER. Whereas if you move towards, let's say, more, let's say, power-generating fusion devices, ferritic steel, ferritic metastatic steel that experience lower swelling under irradiation, and those are also the steels considered for advanced cladding or structures in, let's say, liquid metal neutron reactor, fission reactors, are the dedicated materials, in addition to more advanced, let's say, materials such as ceramics and silicon carbide especially. One specific aspect of fusion devices is, let's say, the type of effect, of damages effect that are generated by the 14 MeV neutrons. Well, this is a very high, let's say, energy neutron compared to fission neutrons, typically 2 MeV. And then this leads to create helium through N-alpha reactions on steel. And then you can see that in terms of helium production, and that causes embrittlement, or in terms of damages, in terms of, let's say, displacement per atom, let's say you can see that in fact the damages caused by 14 MeV are much higher than those produced by fission reactors, and this causes for specific testing of, let's say, structural materials considered for fusion reactors. So there has been quite a significant investment made in low activation steels for fusion devices. And you can understand that because, in fact, the decay heat is just generated by the activated steel. And then replacing nickel or molybdenum by manganese or by tungsten really achieves, let's say, lowering the activation. And this led to develop, let's say, a family of steels called Eurofer. And in fact, let's say, dealing with low activation steels also contributes to lower the decay heat you have to deal with when you shut down, or you have to deal with in case of accidental events. Let's say more, let's say, advanced materials like vanadium alloys or silicon carbide or other ceramics are also considered as a very low activation materials, and let's say for future, let's say, for future progress for fusion devices. Fusion devices, let's say fusion was also one of the precursors in considering ceramic as an idealistic structural material, both for the protection of the first wall or for the blanket. Well, the emphasis on that might have, let's say, diminished a bit, at least in Europe, but I think that there are commonalities in the interest of developing, let's say, advanced ceramics that could really survive a harsh environment in terms of high temperature and in terms of irradiation. And in fact, for fission reactors, currently the interest in ceramics really relies on, let's say, accident-tolerant fuels, and then having really fuels that keep their integrity or keep their geometry in really fairly advanced phases of cooling accidents. And there are commonalities of interest in this type of advanced material. So we've spoken of low activation steel. So specific materials for fusion also include, of course, the lithiated material, the lithiated material that is really used to regenerate the tritium. It can be either liquid, like the lithium lead eutectic, and I've shown one of the sketches, or it can be solid, like titanate or silicates or aluminates. And then you have to figure out that a blanket could be like a fission reactors with fuel element replaced by, let's say, silicate of lithium. But not only let's say this medium is really the area where you regenerate tritium by capture on the lithium, but it is important to extract online the tritium. This means like exhausting the fission products of, let's say, of a fuel pin within a fission reactor. And you see the complexity of this, or the more that in order to do that appropriately, so while minimizing the amount of piping of structures that would cause parasitic neutron captures, this requires to really keep the solid or the liquid lithiated material in appropriate temperature range for the tritium to be the more easily exhausted. So you see the complexity and therefore the need for appropriately designing the blanket with the same tools that are being used for fission reactors. Regarding technology, there are commonalities with fission reactors. So there are heat deposition within the blanket, there are cooling, and in terms of materials, in terms of piping, in terms of, let's say, systems, there are a lot in common. There are a lot in common between both systems in terms of engineering of components, and also in terms of interest into compact heat exchangers, for example. Well, because the space is very scarce, I would say, within the blanket, the surrounding area of the plasma. So there are commonalities in interest in some components, like very compact heat exchangers. And compact heat exchangers having helium, for example, on one side, and liquid metal or water on the other side. So stamp plate heat exchanger or brazed, let's say, plated heat exchangers are really considered for compact heat exchangers for both type of devices. So you have on the left one of the devices that were considered for our program, Astrid, fast fusion reactors with a gas turbine. And you have some equipment that is on the right of the slide that is considered for some fusion devices. So having commonalities in the component design in terms of, let's say, materials or family of materials, of course, drives commonalities in terms of codification for use of these materials in nuclear devices. And then in the first step, because, let's say, ITER is mainly using austenitic steels, so the codification code that was developed in France for the fast fusion reactors has been extended, let's say, for the use of ITER. And further beyond that, in fact, the code RCCMR that had been developed for fast fusion reactors and that in fact merged with the codification for experimental reactor into the RCCMRX has incorporated provision for the Eurofer, so the low activation steel. So as, let's say, to be prepared for the design of, let's say, the next step beyond ITER, so the demo type of reactor. So codification to comply with the regulation for the licensing, let's say, require this, the extension, I would say, of the mechanical design codes. Now, very briefly, in terms of, let's say, inspection, in-service inspection and devices. So both fission reactors and fusion fusion devices with ignited plasma have commonalities in being, let's say, hostile environment in terms of temperature, in terms of irradiation, in terms of not accessible, let's say, medium. And for Phoenix, for example, that is filled with sodium, this is an opaque medium, and a demonstration the integrity of the core supporting structure really required to develop ultrasonic devices or, let's say, X or gamma tomography, so as to really have access to the checking of the integrity of the supporting structure without having a direct vision of it. Like for light water reactors. In light water reactors, you just take all pieces out and you have a direct inspection of the vessel and you can really check every weld. Of interest are the devices that have been developed really for, let's say, well, to proceed with measurements in the plasma, in the fusion devices, both, let's say, as plasma diagnostics or just for checking the integrity of the structure. And you have an example with this infrared endoscope in Torsupra. And we will see that this might have some interesting spin-off for fission reactors. In terms of remote maintenance, in fact, robotic arms have been developed for, let's say, maintenance in hot cell for fission, and then, in fact, the same type of device could be adapted to the complex geometry of a torus and tokamak. And in fact, this arm has a capability to, let's say, bring some device for visualization as well as some tool to proceed with some operations like welding, as you can see here. This is a kind of snake that can just ramp, let's say, in the toric space of the tokamak. So in fact, you see that a lot of technologies of devices that have been developed for fission apply to fusion with ignited plasma. Also, there are feedback from fusion. And I told you that ceramics, for example, had first been considered in, let's say, in fusion devices and currently have an interest in fission reactors. So some of the diagnostics, like infrared diagnostic to really measure temperature on the first wall, also have some applications to detect anomalies in, for example, steam exchangers. So there are feedback from fusion to fission. And there are commonalities also in, let's say, using, let's say, virtual reality for preparing interventions in a complex environment. And this is used for fission mainly for dismantling and really for preparing for dismantling, where robotic devices will do the job and where the human cannot go, just to check whether the operation that is planned is feasible. So this virtual reality is capable of really checking the feasibility of the intervention before actually doing it. And you can see that, in fact, the same, let's say, the same technology is being used to plan for interventions on the fusion devices. Last, maybe the use of laser-induced breakdown spectroscopy, which is a very powerful mean that uses a laser that really shoots at one wall. And then, in fact, by the spectroscopic analysis of the light that is the plasma generated, you can re-derive the content, the chemical content of the wall. By the way, this has been used, let's say, by one of the rover Curiosity on Mars, really to just analyze the nature of the rocks on Mars. And then for the fusion, it is used really to measure especially the tritium content on the first wall, and to assess for the radiological ambience as well as the hold-up, tritium hold-up in the first wall. Last comment I wanted to make, again, regarding tritium. So the need of tritium in terms of amount for ITER is typically kilograms, and I told you that in fact the tritium is coming from CANDU reactors in Canada. So how much of tritium will be needed as a hold-up for the demo reactor? This is the next step, probably in the 2014, that is expected to fully demonstrate the capability of producing power and at the same time demonstrating the effective regeneration of tritium with a full coverage of a blanket, probably above 10 kilograms. So how this tritium will be made is, let's say, an issue. And certainly fission reactors will be needed, I would say, at least to produce the initial load, even though, let's say, it is expected that, let's say, the demonstration reactors and those to come afterwards will have the capability of self-sustainability in terms of tritium, let's say, generation. And as I've said, this is key, because there is a need for some makeup of tritium, so the supporting fission reactors that are needed will be, let's say, more than the equivalent, let's say, power generated by fusion. But this is the next step beyond ITER. This will be an objective of demonstration of the demo. And currently, there is a European Commission that, by the way, my colleague Christian Rizela is co-managing, that really addresses tritium technology to really appropriately design the tritium systems that are needed for fission reactors. So in brief, I wanted to give you some insights into, let's say, reasons why there are commonalities between fission and fusion devices. And in fact, I've covered 5 types of synergies. Certainly the blanket has a lot in common with fission reactors, and in terms of design codes, in terms of technologies, in terms of codification, in terms of safety demonstration, except for reactivity, but for cooling accident or for the confinement, they are really very similar, let's say, requirements. And then the requirement of licensing, let's say, future, let's say, fusion devices with ignited plasma are really required to use the same, let's say, codes, the same technologies, and the same techniques, I would say, for, let's say, maintenance and repair in hostile environment, as well as for the dismantling and waste management. So, and there will be increasing synergies with fission as we progress towards a demonstration or an actual reactors that will actually generate the power, because of the amount of tritium, because of the significance of blanket and the decay heat to be dealt with, and then there will be increasing synergies. Fusion is an extremely, let's say, promising and an interesting field of research and demonstration, all the more that it is very appealing to students. And I'm very pleased that, in fact, there are so many commonalities, so that, in fact, those, let's say, young scientists that embark on fusion really also develop some interest and knowledge in fission, and vice versa, that, in fact, a lot of people like me who grew up in the fission side, let's say, brought what they could on the fusion side. And then I'm so very pleased that, in fact, to see a greater, let's say, a greater integration to come between fusion and fission program within Europe, and let's say also more widely at the world scale. Thank you very much for your attention.
Thank you very much, Dr. CARRE. Questions? Please. Please introduce yourself with name and organization. Sure. Thank you.
So I'm William Nuttall from the Open University in the United Kingdom. Thank you for the presentation and the themes around fission and fusion, and particularly on tritium, and that's where I'd like to go. So here we are in Romania, in the European Union, And Romania is operating 2 CANDU-6 reactors, and as I recall, is contemplating tritium removal and addressing the tritium issue for worker safety reasons, with no connection at present to fusion at all. But this is a European resource for the future of fusion. I was wondering if you can confirm my understanding and comment on this reality.
So I maybe pass, let's say, the right of answer to my colleague, Christian Grisella, who is really addressing fusion, the tritium issues in terms of fusion. But certainly I would see value on the situation that you described.
This is not completely true, I can say. I remember when I was task force leader at JET, dealing fusion technology activities, we have a strong relationship with people from Romania, especially on the detritiation, water detritiation system. I remember visiting a plant here with money coming from Eurofusion. At this time it was EFDA, and the plant was in Valcea, and the people are deeply involved in fusion research. This was 15 years ago, something like that. Now they are involved in the project that I am managing, and they are deeply involved and part of the project. So we are interacting a lot with people from CANDU. Okay,
Thank you.
I'm pleased that my presentation gave you the opportunity to establish connections. What is this synergy?
Other questions?
So when we talk about synergies, so I would expect that, let's say, key problems in both sides in fission and fusion can be better solved when you have this integrated program. You have not addressed such key problems in your presentation directly, but I guess there are many.
You mean in terms of education and training?
Yeah, and no, not only that. I mean, I'm talking about technical key problems in both areas. I mean, when we talk about fusion, so there are for sure challenges, and in fission there are also challenges. And I would expect in such an integrated program that our synergies activities that both sides will take profit in the term that they can solve their own problems when the others help them.
So I'm not sure to have the appropriate answer to your questions. So we had example yesterday, or for example, European programs that address, let's say, issues that are common to fusion and fission, and especially in the field of materials. I think they are fairly advanced, let's say, programs that really addresses both issues. For what regards robotics or maintenance or so, I think this is really a matter of engineering, and this is really, I think, the projects that are directly dealing with the companies or with the laboratories that really develop or manage the appropriate technology. I'm not sure to have the complete answer to your questions, but if we can discuss at the pause if there are remaining questions.
But I guess it is a topic for the discussion later on.
Okay, good.
So it's good.
Thank you. We have another question here.
Hamid, thank you, Frank, for very interesting overview. I think the first point in your summary, the nuclear design and technology, deserve, especially from the fusion people in charge of the design of the demo reactor, to really interact more deeply with the people designing the reactors, because it will have certainly impacts on some fundamental choices. Among others, you pointed out the difficulty for the tritium, which is a big concern that we have to produce it in the TBM. Then the technological choices for the TBM can be very appealing when you consider the TBM alone. That there are solutions that look very appealing, but when you integrate them in the reactor design, you end up with kilometers of pipes of helium, and I'm not sure that this is something manageable from the design of the reactor when we know the difficulties of helium confinement in our gas-cooled reactors. And so therefore I see a lot of synergies there of, let's say, exchange of experience from both sides that will be very beneficial. I don't know if this is triggered today enough between the two teams or the two worlds.
Well, maybe two, three comments, and again, I may not be the best person to answer that, but I think there are demo studies that are conducted at least at the scale of Europe or even beyond, and I would hope that within this context that there are appropriate, let's say, exchanges between, let's say, experienced people in fission and fusion, or at least this is the right direction, and maybe Christian might comment on this issue. Secondly, regarding the blanket, which is really a key component for, let's say, fusion reactors, so the complexity depends on the nature of, let's say, the lithiated material. So if it is liquid, you could expect, let's say, a lesser, let's say, complexity. If it is liquid, like, let's say, in one of my slides, you do not this piping to remove, to have this online sweeping of the tritium. You can have some bubbling, let's say, in some remote part of the blanket. So the complexity depends also of the nature of lithiated materials. Also, there could be situations where the technologies that are being used for ITER might not be extrapolable to demo. And this is very interesting. And I'm thinking, for example, of the first wall of ITER that is covered with tungsten. And then, let's say, tungsten, let's say, is good for resisting sputtering, and therefore this was one of the reasons for choosing this material. However, this is a quite significant Newton absorber, and it is likely to jeopardize the tritium breeding ratio if you would it at the scale of a demo reactor. And then we know that carbon tiles or silicon carbon tiles do not do the job because of, let's say, the retention of tritium in the current technology. The hold-up of tritium would be too big. So let's say material, this is material issues, and there is a need to invent, in fact, the type of, let's say, protective materials or first wall material that be used for demo, knowing that tungsten is not extrapolable for what I've said, and certainly for the price as well.
Thank you.
Christian, do you want to comment just shortly?
Yes, I want to comment, and I want to comment, but consider that I am speaking by my name. I am not speaking from my organization, CEA, I am speaking ad personam, okay? If you look at the difficulties that we have on ITER at the moment, it's come from two things, in my point of view. The lack of engineering expert from the beginning, and the lack of licensing people from the beginning. And I hope that in the future, especially for demo, this will be corrected, because this is a real problem, and we come from the discussion yesterday that you put on the table, or someone put on the table, that the people from fusion doesn't know what is happening on fission and doesn't integrate things. But you have to remember that the machine is complex. The people that operate the machine now are physicists like me. They are not engineer and design people. They are all retired, because JET is operating for 30 years, Torsupra is the same. So you have lack of people aware of the problem. And first, this is the first point, and the second point that now we are coming to nuclear installation nucléaire de base, and this is completely different from the past. So, in my point of view, we have to consider the difficulties that we have to in ITER to increase the level of integration of people from licensing and nuclear engineer, especially for the design of demo. But I am speaking from ad personam. Please consider this ad personam, okay?
Thank you very much, Gérard.
Yes, thank you. I have a question to Franck. You mentioned in the third bullet education in nuclear physics and engineering. Fusion is a very attractive domain for young generation. How fission could beneficiate of fusion, of this attractivity for fusion to get the best student or the best young scientist? What could be your recommendation in that field?
Well, I'm not, maybe not the best person to answer this question. Well, so far, let's say fusion education was based on plasma physics, and I think it still is. And so that, let's say, education is separate from, let's say, the education from nuclear engineering. But I think, this might happen, I might not be aware of it, that because of these increasing synergies that are needed for, let's say, experimental reactors like ITER or the further demonstration to come, there may be more, let's say, interactions between curricula and between educations. And at least within the teams that really work on those projects of experimental reactors or fission reactors, this really triggers, I would say, cross-cutting exchanges between, let's say, the communities of fission and fusion. And I think that contributes to, let's say, have maybe moves in both sides. Let's say to have some of the students interested by fusion, developing some knowledge in fission, and to have some, let's say, people experienced in fission technology interested in application for fusion. And I would hope that at some point the same would happen for, let's say, nuclear fission reactors and renewable energies. And I had experienced myself, let's say, students, let's say, embarking into, let's say, energy, low carbon energy major in the engineering school, Polytechnique, for example, and saying, well, I'm interested in renewables, but I want to know about nuclear because it's so exciting regarding the interdisciplinarity. And then I would like to do renewables, or vice versa. And in fact, I knew some students who really went from one area to the others. And then I would hope that there are even more commonalities, I would say, between fission and fusion. I would hope that at some time in a few decades, we would have a nuclear community that would consider, let's say, would address specifics and commonalities of both type of, let's say, nuclear energy.
Thank you. The last question, please.
The question is a small contribution to try to address what I think is a real problem, again, at personal level, but not only at personal level, because actually, you know, at the IEA, we have very limited activities on fusion. At the moment, they are placed in the Department of Nuclear Science and Application, not in the Department of Nuclear Energy. This is also a significant issue. However, the Director General has recognized that there is the need of a close cooperation between, even within the agency, between the fission community and the fusion community, which is actually very small, in particular to address the issues that you have raised, safety approach, licensing, some technology that are commonly used in fission and for which, of course, fusion can benefit. So in order to promote this kind of internal cooperation also at the international level, has just established an internal coordination committee where all the departments are represented. So it means that in particular from the Department of Nuclear Energy, there will be very significantly, the section head, by the way, is here at the conference of waste technology, because there is a specific topic on waste technology which has to be addressed with innovative techniques which are already in place in the fission context. There is I myself, because I'm the section of advanced reactors, so of course all the advanced technology which are being used for advanced reactor can be also transferred to fission. And more significantly, there are all the representative from the major section of the Department of Nuclear Safety and Security in order to start talking about the safety approach and in view, of course, to develop in the very future safety standard for fusion device. Another point, also the Department of Safeguard will be present, because in any case these are very high intensity neutron source, okay? And with neutrons you can do many things also, which can be problematic from the proliferation viewpoint. So just as a small contribution.
Thank you.